So
yeah, no
anyway,
one likes the way it cuts for you, Alessandro. We've had multiple comments about that.
So just to do the concept a bit, maybe probably you guys are familiar with the Merkle trees, but just to reintroduce them again, a Merkle tree is somehow a sort of accumulator. It's not really called an accumulator, it's more of a vector binding, but it's somehow a way of, if you want, collapsing a whole set into a single value. And somehow this single value can be used to verify some properties of the set. So for instance, you can verify that a certain element was part of this original data set. And the idea with these Merkle trees is that you can use them, for example, again, Bitcoins. In every block header, you store a root, which is calculated from the transactions contained in the block payload. And then somehow you can have these efficient proofs of inclusion for any transaction into the block header. Because basically you can request a proof that corresponds just to the path along the tree to recalculate the root starting from the transaction that you're actually querying.
So you got like a log.
I don't know, maybe I should have said it. So you basically take this data set and you start pairing each element in the data set and dashing them together in a binary tree. At least that's what you do. And you repeat this process until you reach the top node, which is the Merkle root of your tree. And then basically, you know that starting from any one of these elements, you can recalculate the root if I give you the elements along the path. And the idea is that there will be only log n elements in the path, while if I wanted to verify in the dumb way, so to say, I should have downloaded the whole data set, which instead scales like n rather than log n. Mm-hmm. Right? Okay, so this is the idea for a vector binding, or let's say just a tree, where the order of insertion in the data set is important because it would change the root if you switch two elements, right?
Yes.
These accumulators, if there is a question, just interrupt me. These accumulators, the idea is very similar. You want to collapse a data set into a single element, right? That then you can use maybe to verify some properties of the original data set. But the idea is that these accumulators have this additional property, this quasi commutativity. In short, it just means that the order of insertion in the data set or the order of the elements of the data set does not change the final root, if you want, that you get, the final accumulated value.
Is there an extra condition of what can be called an accumulator? Or like literally the whole data set is a trivial accumulator? Or do you need some security properties?
Like privacy.
Mm-hmm. No, privacy is not a requirement. What is a requirement is consistency. So let's put it this way, it should not be possible to create a witness for an element that is not part of the data set.
So a witness,
and then you have this
a witness in the case of the Merkle tree would be the path from the leaf to the root, right?
Yeah.
Okay.
So sorry, can you repeat?
So again, a Merkle tree is not strictly speaking an accumulator in this sense.
Yeah.
But the mutatis mutandis, that would be, let's say, the witness. And also you have some extra properties that you can impose, like collision freeness, as I don't know if they define in this paper, where basically you cannot create a proof of so you cannot create a proof of membership for something that is not in the accumulator. You cannot create a proof of non-membership for something that is in the accumulator.
Maybe
so I mean, these are just intuitively speaking, this should work. Basically, you should be able to have no false positives and no false negatives somehow, right? I mean.
So I think we discussed this later on, but so what are the requirements for an accumulator? Sorry, because just to nail it down. So the accumulator is, you want to somehow take data and then be able to prove that certain data is an element. Okay, sorry. Apply some function to some data and then be able to prove that a piece of data is contained in that original data or not.
Maybe we can show
basically
the example.
This is the definition. Like the definition that I'm aligning here is basically the definition. You want to condense a set of values into one short accumulator, so in a single value, let's say, and there is a short witness for each value that has been accumulated. Here, short means efficient somehow, okay, which we'll understand straightforwardly. Sorry, what that means. but basically means that it does not scale like the length of the data set, because that's a trivial witness, right? If I give you the whole data set, that's a witness for any element.
Sure.
So you want somehow to have some short witness in some sense, right?
Okay.
So for a Merkle tree, let's say, again, it's not necessarily an accumulator, but it would be log n, so it's short in that sense. For these RSA accumulators, it's constant size, the witness, so it's even shorter. It's
so
just one number.
Why is a Merkle tree not an accumulator?
Like regular dense Merkle trees are vector binding somehow because the order of insertion matters.
Okay, so here the order of insertion cannot matter for accumulators.
Right, somehow, because they have these extra properties of quasi-commutativity.
Okay, so for accumulators, they're commutative or quasi-commutative.
I don't know if they define the quasi-commutativity in this paper, actually. I thought so, but maybe they don't. But basically, okay, I can define it on the fly.
Look at okay, and once you do that, we should do the the two use cases there.
Yeah, right there. You just passed them.
Why? I would go through the paper first. Like I think the use cases kind of interesting part of the paper in a sense, because I think they're a little bit cooked up. I think the interesting part is this proof of non-membership somehow, which is it's a nice idea, on top of the Rsa accumulators that you have. I mean, also this paper now, it's pretty old, right? It's somehow standard. Like it's been surpassed by, there are other papers that discuss even extensions of these, like
the author?
to batch stuff and so on. But sorry, say it again.
Who's the author and when was it published? I think we didn't mention that.
I think it's 2007, and authors is Li Xu.
Got it.
To remember. Don't ask me to distinguish the two Li's though.
Okay, but I mean, maybe we should look at the example, right? Just to I mean, even if it's dumb, it'd be nice to see why it's dumb. Like I thought it was an interesting use case. Here, suppose a credit report.
But these examples, they're cooked up. Like these are examples just for these universal accumulators that I think are not even, I mean, intuitively, obvious. But okay, sure, we can go through the example as you guys are the.
We're the host.
How do you say? The host.
Harry, you should do the example.
Let me think about a couple of famous hosts. I don't know.
Bob
Anyway.
Barker.
James Corden.
But they're not like, a couple. I don't know what to say. Anyway.
Okay.
So these two examples, they want to give an example where these non-membership witnesses are useful. But I would go in order. So let's go in order with accumulators. I'm also scrolling up and down. It's terrible for.
In the comments, it's going to be like, please do this.
Like your mom is going to hate this, Carlos. So again, let's start from the beginning. Let me just get up to end of section 1. I promise I'll do the examples. So you have these accumulators. You want to condense a data set into a single value, and you want to have short witnesses for elements of the original data set. So there is going to be, in general, a verifier that is going to ask a prover for a proof of inclusion of a certain element into the original data set. And what the verifier holds as initial data is only, obviously the element that they want a witness for, and the accumulated value, the accumulator, let's call it, okay? So this is in general the definition of an accumulator. In an extension of this definition, then we can define a dynamic accumulator, which is basically an accumulator that supports update of the original data set. So you start from a data set, you create an accumulator, and then you can keep adding new elements or deleting them, and you can update the accumulated value efficiently. Okay. So up to now we said you have accumulators is just a data set that you can condense with a witness for any element in the data set. Dynamics means that you now support update of the data set. And now what we want to add to this is no membership witnesses. So now on top of having a witness for each element that has been accumulated, I will also have a witness for each element that is not part of the data set. And that's why adding this property means that now these accumulators are universal, because now you have you can prove either inclusion or non-inclusion for any element.
But then, so are these sets finite, or it's like any possible value can have a witness? What's the domain, I guess?
They're not. They don't have to be finite. Okay. in the specific instance of RSA accumulators, the original data set comprises only prime numbers. Are they, which they're not finite, like there are an infinite number of prime numbers. So in general, they don't have to be finite data sets, right? Okay. Now for the applications of these no membership witnesses. Sorry,
Ali, could you zoom in a bit on the PDF so that it fills the page there? Just give it a little.
Say it again. Sorry.
Just zoom in a little bit. I can't see the text; it's a bit small.
Better now?
There we go. Yeah, our audience likes nice big text.
So you have these two use cases. Well, basically, there are situations in which you want to show that you're not part of a data set.
Sure.
So here they do. Yeah, it makes sense. But yeah.
Especially in the COVID times,
COVID,
right?
Exactly. You don't have COVID. Like the data set could be who has COVID, right?
Right, but the idea is that in the previous constructions, the data set is who doesn't have COVID, and you can prove inclusion of the data set of who doesn't have COVID. So effectively, you have the same, result. The difference is that maybe these two data set, one where predicate P is true and one for which the opposite, not P, is true, right? They could have vastly different sizes. And in this sense, it must be more convenient either to give a witness of inclusion for data set with a predicate P, or a witness of non-inclusion for the data set with predicate not P, right? So that's kind of their idea. Like, you could do the same even only with membership proofs, but sometimes it's more convenient to have no membership proofs.
So at this point, there's no, I thought maybe this was calling for some kind of privacy, right? Where like
that's a different question.
Yeah, I guess. So this is really just an argument from efficiency.
No. So yes, I mean, I guess it's also a nice, result. But they also construct a zero knowledge proof for these non-membership witnesses, which again is something that you kind of can do with these accumulators, especially if you have these RSA accumulators, or if you have, elliptic curve pairings accumulators, stuff like that. You also have some algebraic properties that you can prove with these accumulators in a zero knowledge fashion. So maybe just to give some context, the idea of a zero knowledge proof is that it is possible to prove a predicate, let's say, or an algebraic property of a value without revealing the value nor the witness of the value. And in general, the idea of the zero knowledge proof is that there is first a commitment to something, and then there is a challenge from the verifier, and then the prover can show that they can solve the challenge, and somehow the commitment guarantees that they did not make up the answer after the challenge was posted. That's a very rough idea, but I don't think we will have time to go into the zero knowledge part today. Maybe next time we can do it. But I would move on, guys, because I think we need some rhythm on this podcast, because it's really... So I would move on to the meat here. So we understood what is the goal of the paper, just introduce these non-membership witnesses and then generalize these accumulators to be universal. Now, there are a lot of definitions here and stuff. I'm just going to explain it in words every time. The important thing is that this is going to be an RSA accumulator, so I'm going to explain what that means. But the only mathematical assumption that they need somehow is the strong RSA assumption. Which, again, okay, so this we don't need. Again, here, you have this nice, this nice equation, but what it means is basically that if you give me a random x drawn from, Zn here, so the integers mod n, it is unfeasible for me to find a basis y and an exponent e, where e is larger than 1, such that this equation holds. So basically, it is impossible for me to find y to the e equal x mod n. So this is the strong RSA assumption, where I can also pick
discrete log problem.
Yeah, I think so.
Well, this is stronger because you cannot pick you can pick the basis here. That's why it's strong.
Oh, okay. Oh, you can pick the n.
No. You can pick y.
Oh, so for any y.
Yeah, I mean, you can choose both y and d larger than 1. Okay, if e is 1, obviously this is trivial, right? So easy has to be larger than 1. And okay, this is mumbo jumbo here. It just means that the probability that you actually, have an algorithm, a universal Turing machine that picks y and d given input n and x, and this n is generated is just, this y to the k just means that it has a certain bit length k, which is your security parameter somehow, is negligible in k. So it's smaller than any polynomial, 1 over polynomial function, right? Mm-hmm. Where k just determines your security input. Okay, this is all we have to remember. So again, mumbo jumbo, right? It really just means that you give me x, I cannot find y to the e. And in reality, what it means is that it's hard to factor numbers. That's it, right? Okay. These I will get to later. So, but let's just take this for, what it is. This is also the assumptions somehow at the base of the RSA protocol, right? Okay, and this knowledge part we don't need. I would just go to the, to the central part here.
The meat.
Again, this universal accumulator. Oh, here you have the quasi commutativity, by the way, the property. So, okay, there are all these different properties. We can go through them maybe one by one quickly. I just explain in word what it means. So, efficient generations, it just means that you can basically compute the accumulator efficiently somehow. The efficient generation and the efficient evaluation somehow. This auxiliary information here is, for us, is just basically the factorization of n, which is the modulus of the RSA modulus that we're using. So I'll get to that in a second. Quasi-commutative is the property that I was mentioning. So given two elements x1 and x2 into the data set xk, where k again is your bit length basically, right? For each of these accumulators, so this f here is the accumulator function, let's say, it holds that if the result that you get if you first accumulate x1 and then x2 is the same as what you get if you first accumulate x2 and then x1. Okay. Where g again here is just a parameter, and this g will just be the basis of our exponentiation. And then, as we mentioned before, we have membership witnesses and we have no membership witnesses. Okay. That's it. So notation W1 is going to be a membership witness, and row 1 is going to be the verify membership witness, and row 2 is verify non-membership function. We'll get to that.
Just to be clear,
security, it just means that you cannot find bad witnesses. The probability of finding bad witnesses goes like a negligible function of k. I would say it's really words perfect. In other words, it is computation infeasible to find both a valid membership witness and a valid non-membership witness for any x in xk. So it's also called collision freeness.
Alessandro, I think Perry had a question.
Yeah, please.
Sorry, just to be clear, these witnesses are just the pieces of data that you supply to the person asking you to prove your membership or not.
Yeah,
it's a way that
yeah. Sorry,
okay.
Go ahead.
No,
so that's it. Okay. Yeah. We'll get to it like in practice what these witnesses are, and it's going to be super clear, okay. Right? I mean, here again, there are some details. Let's just go to the definition of these RSA accumulators. It's just simpler. Basically, what you do, your accumulator of G and X, where X is the data element you're accumulating, and G is just a parameter, in this case is the base, is just going to be G to the X mod N, where your parameters here are this N, which is the modulus of the RSA modulus of length K, and it has to be a safe prime, meaning that it's the product of two primes that you can write in this form, basically, where P and Q have equal length, and they're all prime numbers. I'm not even sure these are a requirement anymore, because I think the requirement for these is because there is a factorizing algorithm that doesn't work if you have safe primes somehow, but it's not a number sieve, and the best is a number sieve. So somehow this is pointless anyway. I don't remember, and this is a detail we're not sure about. Okay, and this G has to be part of an element of the quadratic residues of n. And obviously, it doesn't have to be 1. Okay, and then that's it. Basically, you take G and you exponentiate to x mod n. So in this way, you can define this accumulator C to be just G to the product. Where does it define? Do they define it actually? They don't define it yet. That's super weird. Okay, but basically G is going to be C. Sorry, the accumulated value is going to be G to the product of all the x's in the data set. Well, this is the idea here. If these x's now are all prime numbers, right?
Sorry.
This resulting product that will be the exponent.
Won't
get in there, Perry?
No, but won't you? You go ahead. Yeah.
Let me finish and then I'll get there. So the exponent that you get is going to be a very large number, but with a unique factorization, right? Because all these elements in the original data set are prime numbers. So each number has always a unique prime factorization, right?
Yeah.
Okay. And in particular, these prime numbers will be all different from each other. And that means that I can give you now a membership witness CX, which is just G to the product of all the elements in the data set, but the one that you're asking a proof of inclusion for. And then I can quickly verify that that element is part of the accumulator just by exponentiating my witness times the element x, and then verify that I get the accumulated value. So basically the idea is, apart from the exponentiation and so on, the idea is I prepare a number which is just the product of many prime numbers. You give me a number and I give you this product, but where I divide by the element that you want to verify, and you just remultiply and you see that you get the same number. The fact that we exponentiate here is just to make the computationally infeasible to actually calculate this thing, right?
Sorry?
Is to make it, how to say, no, well, we exponentiate here because we want to mod n, so we want this to be of a constant size somehow. Yeah, that's, I think, the final goal at the end. Okay, so this is the membership witness. Is that clear how that works? Again, you just give G to the product of all the elements in the data set, but the one you're verifying. And then you just redo the exponentiation and you check that you get the accumulated value. For non-membership witnesses, we'll get to there, but basically the non-membership witness uses the extended Euclidean algorithm to output these Bézout coefficients so that then you can verify. So given A and D to be the non-membership witness, you can verify where D is a basis again, and A is just an integer. You can verify that C to the A is equal to dx, D to the x times G. Sorry, mod n. And we'll get to why this works in a second.
So sorry, Alessandro, though. You see this, I don't get why it's the product of all the elements of the set. From the original definition of quasi-commutativity, it seems like if you wanted to take f of g of x, comma y, that would equal to g to the power of like gx to the y or something. It looks like there's two exponentiations you'd have to do. No?
No. So maybe we'll get to how you update an accumulator in a second. So to the dynamic part, maybe, and that's simpler. But it works with the quasi-commutativity. Now, it's very difficult to do stuff without a whiteboard here, but okay. I mean, it is also easy to see that f is quasi-commutative. I mean, because product is commutative, right?
Yeah, but it seems like don't I have to put? Okay, no, I see what you're saying.
Right, because you get here
G to.
this G to the X1, and here you get this, and you do to the X2, so you get the product. Okay.
And you're saying, yeah, okay, it's fine. Yeah, cool.
Okay, so, okay, this is actually an important remark. This section here is actually pretty important to me. Like, I think because in the original construction of this dynamic accumulator, you don't need to publish G. You just need to publish C and the witness in order to have these short proofs. Now you do have to publish G because G enters also in the non-membership verification. So now the basis is part of the public parameters of your construction. And somehow they rightly say that if a party has a suspect that he has some, some sensible guesses for the data set, they can actually check what is the data set now because they have G, right? While before for the strong RSA, you couldn't without G actually get the accumulator, like you get the exponent that gives you the accumulator. And that's not really a problem because, first of all, in some cases, you don't have to actually hide the accumulated values. Like, I don't know, for a stateless blockchain, you don't care about actually hiding the data set. And also, if you really want to hide them, you can just add a random value to the set so that it hides all the other values, again, via the strong RSA assumption. Okay.
By the way, guys, sorry, Ale. In 5 minutes, I'm going to have to reset the call. So if you want to find like a graceful place to take an intermission, that's keep that in mind.
Sure. Let's move on, I would say. So now they explain how you can how you can compute these witnesses, membership and non-membership, in the two cases. Either if you don't have the auxiliary information, which again, in our case is basically if you don't have the factorization of n of the RSA modulus, or if you do. Let's start with what you do if you don't have the auxiliary information. This is also the trustless setup somehow, right? There is no trust party that holds this factorization. Again, details, but the idea is that by definition, G and X is equal to G to the U, where this U is just the product over all Xi in X, capital X. So this is the accumulator. To calculate a membership witness, you just calculate Cx, which is G to the U over X, right? Mod n. Where basically this means that you just take this U over X is just the product over all Xi's that are not equal to X. And then to verify the witness, you just do Cx to the X and you get X, C mod n. So far, so good?
Yep.
If you want instead to prove non-membership by the, okay, what you know, I want to prove that X is not part of this capital X data set, right? Mm-hmm. Now, that I should have stressed before, in order for the RSA accumulators to work, okay, it's not strictly a requirement, I mean, but let's take it as a requirement now. This data set, the elements of the data set have to be prime numbers, right? So that there is a unique factorization, because if you don't use prime numbers, then you can have kind of witness for elements that are factors of an element in the data sets, right?
Well, they have to be co-prime, I guess, to the modulo, to n, right?
No, they have to be prime numbers, because if you're not prime,
yeah,
it means that there are two integers, a and b, such that x is equal to a times b, where a and b are both larger than 1, right? I mean, just the definition of not being prime.
I mean relatively prime, they have to be only to n, because you're in modulo n, right?
No, I don't think so. So let me finish maybe. So if you're not prime, it means that there are two AB. I can factor this number in at least two numbers, right? And then I can give you a witness for A or a witness for B just by multiplying all the elements, but the element that you're factoring times B, for example. And then I created a witness for an element which is not part of the data set because A is not part of the data set. A times B is part of the data set.
Mm-hmm.
Okay, so this is not a big deal because you can map arbitrary strings to primes. There are several ways of doing that. We can go through some of them if you guys want, but I mean, we can just say, let's just say that you can always map efficiently, let's say, arbitrary strings, byte strings, if you want, to prime numbers. Okay, so let's take that for granted, I would say. So you build this data set with only prime numbers. Now, I was talking about the non-membership witnesses, right? So I have an X which is now not part of this data set, capital X. This means that this X, little x, and all the elements in the data set, since they're all primes, right? It means that the GCD, so the greatest common divisor between X and U, where again U is just the product of all the elements in the data set, has to be 1. They're all coprimes because they're all prime numbers. Right. Then you can efficiently find these Bézier coefficients such that using the extended Euclidean algorithm, it's just an algorithm. Don't ask me to explain how it works because I don't remember, Wikipedia. So, but you can find efficiently these A and B such that A times U plus B times X is equal to 1. Right. I mean, okay, there is this detail that actually what you can find with the Euclid algorithm is A prime and B prime such that A prime plus U is equal A times A primes U plus B prime X is equal to 1, and then you can bring A into Z through L by just summing KX. You can always find a K such that A prime plus KX is in Z to L, right? And then you can find this A just to be A prime plus KX and B to be B prime minus KU, but that's fine. I mean, just that it occurs. But the idea here is that you can find this A and B, right? And then you define D to be G to the minus B. Again, G here is your basis for the accumulator. So you do G to the minus B mod N. And then the membership witness for X is going to be A and D.
The non-membership
It could also
witness.
be A and B since G is public, but let's say it's A and D. And then to verify the witness, what you do, you grab a piece of paper. It's a simple calculation. You can verify that C to the A is equal to D to the X, which is the element you're verifying is not part of the data set, times G mod N. And you can check that it holds because by the definition of these Bézier coefficients, right? C to the A is equal to G to the U, which was C to the A, but now A times U is equal to 1 minus Bx, which is G times G to the minus Bx. And by definition of D, this is D to the X times G mod N. Okay. So if this equation holds, then you know that X was not part of the original data set. And the witness in this case is going to be the exponent A and the basis D. Nice. Okay, so this following section is how to compute now the witnesses if you have the auxiliary information. Okay, the take-home message here is that if you have a trusted setup, so you have a party that you can trust that can hold the factorization of N, then you can calculate these witnesses more efficiently. Because then you can do the exponentiation mod phi N. Phi is the Euler-Totian function, so it's just, since let's say N is the product of two prime numbers, so this function here counts the number of integers that are co-prime to N, up to N. And if N is equal to P times Q, for a prime number, phi of P is just equal to P minus 1, obviously, because all numbers are co-prime to a number. So for N, it's going to be P minus 1 times Q minus 1.
Yeah, so
and the idea is that if you hold N, sorry, say that again?
If both P and Q are prime, not any number, just the prime, right?
Yeah. I said if N is the product of two primes, P and Q, then that holds. So the idea is that if you hold N, finding phi of N is tough. But if you hold the factorization of N, then phi of N is trivial because it's just P minus 1 times Q minus 1. And the point is that if you hold the phi of N, then you can do this stuff instead of doing in modulus. Basically, if you hold the phi of N, you can break the RSA assumption somehow because you can calculate roots of the exponent in this mod phi N. And if you can do that, then of course you can calculate witnesses more easily because if I want to calculate a witness for X, I just start from C, right? And I calculated and I take this A, which is going to be equal to the X root. So 1 over X mod phi of N, and then the witness is just C to the A. So again, if you don't have phi of N, I cannot do this. I have to recompute the witness from scratch because I have to do the exponentiation, right? And this is more efficient, obviously. And for the non-membership witness, it's kind of the same idea. what is the take-home message here is that you know that when you set up these accumulators, you have to choose n, right? And it's actually a non-trivial question how you choose n, because if I give you n, then you don't have, I mean, why would you trust me that they don't actually have the factorization? And you know, there is this RSA challenge. Basically, some very large numbers that were published, I think, by RSA laboratories. Okay, somebody in America. Anyway, that's the point, right? Where basically you are challenged to find the factorization of a very large number. And I think that the idea is that nobody actually knows this factorization, not even them, if you trust them. Because the point is that if you are suspicious, you could argue that maybe they do have the factorization and they're breaking the RSA encryption algorithm.
And they're doing some kind of like a Bubka attack.
Why? I would say they're breaking the internet more. I mean, I don't know.
They're stealing your information.
They're spying on you, which they are.
No, because there's a prize, no, on finding these factorizations.
Yeah.
Oh,
that's what you mean. Yeah.
So
there
there's a prize.
Yeah,
they would.
You make a bigger one and then.
Yeah, exactly.
Right.
You don't publish.
But the point is that if you are setting this accumulator, maybe you have a decentralized way of choosing n, where nobody actually controls the factorization. Complex, maybe in some cases, because I don't know, maybe parties are colluding. I don't know. Or you can trust them and just pick this RSA 2048, and there you go. Pretty long number.
I see.
I mean, yeah. Let's go back to the paper. Okay, here there is a proof that this is secure under the strong RSA, which I think works in a way that if you can build a witness for something that is not in the data set, that you're basically breaking the RSA assumption. I don't remember the proof. We don't care about proofs, right?
Sure.
I guess we went through the all general definition part. So we went through basically what is a dynamic accumulator and how you calculate witnesses for membership and non-membership. And now the last piece of the puzzle is how you update this universal accumulator. So we define a universal accumulator and we want it to be dynamic and universal. So we have to put the last piece together. We have to show how you can efficiently update both the accumulator and the witnesses after you accumulate a new value or you delete a value in the data set. And then that will be all. And then there is this zero knowledge protocol that I would not discuss today. So it's very clear and systematic how to approach it here. You basically have to read the section 4.1, which we're going to do together now. Okay, so efficient update of the accumulator. So what that means, again, is that I want to add a new, for example, I want to add a new element into the database. So there is efficient algorithm D in their language such that if C was the resulting accumulator for capital X, and there is now an X hat that is not part of X, then I can run this algorithm on C and X hat and find the C hat such that this is the new accumulator. If instead C X hat was part of the dataset, then I can run this algorithm, passing also the auxiliary information. So this that's the the little footnote. I will explain what that means to calculate the new accumulated value. So basically, this means that I can add an element to the dataset and calculate the new accumulator efficiently just by passing the old accumulator and the new element that I'm adding. This means that I can delete an element from the dataset efficiently and calculate the new accumulator just by passing C, the element that I want to delete, and the auxiliary information.
So sorry.
Basically boils down to the fact that otherwise it's tough to calculate roots. Say it again.
You don't have to know beforehand if X hat is part of X.
I mean, that's the implementation detail, I guess. That's not important. Like, okay, you can have a layer above. You can check if X is part of the accumulator, then you run delete. Otherwise, if it's not, then you run add. But That's
okay. No, but whatever.
That doesn't change the fact that it's efficient.
Okay, sorry. Then I made a X hat is not an accumulator, right? It's an element of the data set.
X hat is an element of the group from which you're drawing elements of the data set. It can either be part of the data set or not.
Yes, but then I want to check if it is, right?
I mean, sure, but that's efficient for sure, right? I mean, that's fine.
Okay, sure.
That's not the point, right? I mean, let's suppose you have two cases. If X is part of the set, then you want to delete it. If it's not part of the set, then you want to add it. But the idea is that in both cases, you can do it efficiently.
I guess the point is someone knows the whole set, right? The person updating this knows the whole set already.
In order to do what?
In order to update the accumulator.
No, I don't think they need to know the whole set.
Otherwise, which one do they do? Do they do D of C X hat, or do they do D of Ox F C X hat?
You can check if it's part of the data set if you have the auxiliary information, I guess.
Okay, I guess I'm not. Okay. There's a way to check.
Because you can run the extended Euclidean algorithm, I guess, to get the GCD. Oh, yeah, but for that, you need the data set is true. I guess if you have the auxiliary information, you can check that without the data set. I'm not sure, actually. That's a good question, actually, maybe. Yeah. I mean, to add some. Okay, I'll think about it. Anyway, then you also have efficient updates of witnesses. So you have efficient update of membership witness and efficient update of non-membership witness, which again means the same thing. Like if I add or delete an element, then I can calculate the new witnesses efficiently. There exists an effective algorithm. Yeah, it's the same thing. Basically, that's what I said in words. And now we can go to the construction. I mean, yeah, okay. So, right, this is the point, right? Of course, you can, if you hold the data set, you can do stuff that is linear in the size of the data set, which is basically recalculate everything, right? But that's not what we mean by efficient. By efficient, we mean that we want operations that are constant in the size of the data set. Okay.
Sorry,
this
Ali,
is
I'm going to ask
definition.
I just want to. What is it about the previous version that made it that made the accumulators depend on the elements in the current data set? Like, why wasn't it not already universal?
Universal means that you have proof of non-membership for elements that are not part of the data set.
Sorry, I meant dynamic. Sorry. Why was it not dynamic already? Like, what was the construction?
Yeah, maybe it was also dynamic, but they're just going step by step.
Oh, okay.
First, they show you how you create these membership proofs, and now finally they put everything together, and they just show you a construction for a dynamic universal accumulator style. Okay. I mean, basically in this section, they show how to update stuff efficiently. Previously, they just showed you how to calculate witnesses.
Yeah. Okay.
Okay. And let's just go direct to their construction. I think is the easiest. So let's start from the easy one. How do you update the accumulator? So you want to add a value X hat to the accumulator. You just calculate the C hat as C to the X hat. That's straightforward, right? You just exponentiate to add an element to the data set. Yep. Sorry, guys, I ate too much for dinner. So if you want now, though, to delete a value X hat from the accumulator to calculate the new accumulator here, C hat, then you need this auxiliary information. Again, if you want to do it efficiently, of course, you can just recalculate everything from scratch. So you need this factorization, because then you need the Euler totem function, and you can calculate this root, basically. You can do C to the X hat minus 1 mod phi n. So this is the catch-up, right? You need a trusted setup to have efficient deletion, unless you are storing witnesses somewhere, right? Because if you think about it, the witness for an element X is exactly the resulting accumulator C hat that you get after you delete X from the data set by construction. That means that if for each element in the data set, I'm also storing the witness somehow, I can update the accumulated I can update the accumulators also in a trustless setup. Like I can update it publicly, so without knowing the factorization event. But of course, then you need to update, once you delete something, you need to update also all the other witnesses, because then what we're saying is that you're going to use these witnesses to actually update future accumulators and so on, right? So I mean, it's a sort of trade-off. You have to store witnesses and you have to keep them updated every time, and it's not explained here how to do it necessarily. It's you need to do something else that we're not going to talk about today. But here, let's say that we're working a trusted setup, so there is somebody that can update these efficiently. Okay, let's move on. So how do you update a membership witness? So W here is the original membership witness for X. C and C hat again are the original new accumulators. So if you add something, you just do W to the X hat, easy. And then you can check easily that W to the X hat to the X is equal to C hat. That's easy. To add stuff, it's easy because it's easy to exponentiate. What is difficult to do is to divide, right? Calculate roots. So for deletion, what you do, you do the same thing. You calculate these Bezout coefficients, A and B, such that AX plus BX hat, where X hat is the one that I'm deleting, and X is the one that the witness is referring to, is equal to 1. And then you can check that if you define W hat, so the new witness, as W to the B times C hat to the A, well, then you can verify that this new witness is a witness for X. You just pen and paper and you verify that this works. Nice. So far, so good. This can be done without the auxiliary information now, this update of the witness, right? That's fine. If I want to update a non-membership witness, so again, C and C hat are the accumulators, X and X hat. So X hat is always the value that I'm updating, let's say, so adding in this case. So you just do, you can get a new non-membership witness, A hat and D hat, which is gonna be the non-membership witness for X, right? By finding these A hat 0, R 0 equal to 1, and then will always the same trick. And then, I mean, you just play a little bit with the algebra. I don't know, I feel weird in describing words what is written on the paper, but basically then you can compute this D hat, which is the updated non-membership witness, and then you can verify that this property holds. Okay, C hat to the A hat is equal to D hat to the X times G model. So again, I can update the non-membership witness under addition of a new element X hat efficiently and without the auxiliary information, so in a public setup. For deletion, same thing, okay? I mean, it's pointless to describe exactly the steps, but you can verify this equation holds. Obviously, if you want to batch together many updates, you just do the same thing where X hat now becomes the product of all the elements that you're updating, either adding or deleting. So what is interesting here, the take-home message, again, is that the update of both membership and non-membership witnesses can be done in a public setup without the auxiliary information. And that's why the trick that I told you before kind of works, in the sense that if you also store in these witnesses, you can also perform this deletion publicly. You kind of have to retrieve that witness and then update all the other witnesses. Right. Okay. Oh, that's all. Nice. So maybe just as a teaser, they now want to, apply these ideas to have zero knowledge proofs that a certain value is not part of a data set. So in a zero knowledge setup, right? So what they have in mind is that maybe there is a certificate revocation, or there is a data set that describes the bad guys or people that are sick of COVID, and you want to show that you're not, but you want to do it in a zero knowledge proof without giving out your element and so on.
Yeah.
And it is possible to do so. It's a bit involved. It's probably more involved than anything that we've gone through till now, and therefore I would maybe do it another time.
Sure. Cool. Can we maybe go through an example of how, like, where would one apply this, say, in a blockchain setting?
Hey, it's a difficult question. So let's say, okay,
Like
you know that Ethereum has a, let's talk about Ethereum 1.0, right? So you calculate the account state, for example, right, using these Patricia trees. So basically the idea is that you somehow condense all the account table in a single value that then enters the block header somehow. But there is someone that holds the account table, and there is someone that can verify then that the route that you're putting in the block header is actually correct. If you use these accumulators, if everyone keeps its witness, their witness updated, they kinda can show, for example, in a stateless setting that they have some balance, for example, because you could say that I map, let's take a super simple case, right? Let's say that I map my account, which only is described only by an address and a balance, right? Mm-hmm. And I map it uniquely, so one-to-one, let's say, to a prime number. I do that for every account, and then I build this accumulator just with this construction, for example. And now if I store this accumulator in the block header, and it gets signed, it's just a block header signed by, it's forged and signed, and so the protocol people agree that by consensus that it's the correct block header. Now maybe I can send money to you in the next block just by showing you that my address, so the one that you get for the transaction, has enough balance to send the transaction, because now I can show you, okay, look, this is my address, this is my balance, and you can verify with my witness that I also put as part of the transaction that indeed I'm part of the accumulator that is the last state root.
Okay. Couldn't you?
Okay. And now you can verify that that is the case. You can process my transaction and update my balance. You can calculate my new value. You can delete my previous value from the data set, and you can put my new value, so you can update publicly the state root. And I can update my witness, and in the future I can send a new transaction with my updated witness and so on. And nobody has to hold the state, actually.
Sorry,
you can just do that.
So sorry, you're not saying like the accumulator would be an account, and the members of the data set would be the transactions?
No. So the members of the data set is the account state somehow. Okay, of course you need both the address and the balance, maybe in this simplified example. So let's say you take the address, you take the balance, that's a bit string, right? And you map it to a prime number, and you get 13, how lucky, right?
Okay.
Okay. But Carlos has 15, no, 15 is not prime, has 17,
yeah.
And I have 23, right? And again, if you had a different balance, instead of 13, you would get 37, but you still would get a unique prime, right?
Okay. Okay.
So now in your transaction, you say, okay, this is my address, this is my total balance.
Mm-hmm.
And you can use these two information to calculate 13.
Yep.
And this is my witness. And my witness is just going to be G to the 15, to the 17 times 23, we said, right?
Yeah.
And then what you can do, you can take my address and my balance, get 13, do G to the 15 times 17, which is just a single witness, a single number that I give you, exponentiate, and check that you get the last account state.
I see.
And so basically, starting from scratch, from an empty blockchain or whatever, from an initial state, that's not important. From an initial state that is just an initial accumulator, an initial set of witnesses, mm-hmm. You can always update the accumulator, update the witnesses, and move on and process transactions every time.
And this saves you how? Because now you're saying...
nobody has to hold the state. Somehow
Okay.
That's the idea. Which, maybe is not even the problem. Because sure. The state is not necessarily what is large in a blockchain, right? But
it adds some sort of...
It's also cool, right? And it's also zero knowledge ready, maybe. That could be useful. I mean, you need something fancier than that, but okay. Maybe not even too much. And stuff like that.
What's the complexity of these procedures? Do you know?
I mean, we said it, right? So
it's exponentiations. Oh, it's constant always?
Yeah.
It's efficient.
I mean, a Euclidean algorithm maybe is log.
Yeah. So
it's linear in the bit size. So it's a log X kind of. So it's still log. In a sense.
What's the advantage of having a Merkle tree? You know, just going back to that original example, since this is like permutation.
Merkle tree is not constant size, right? Merkle tree.
Yeah, exactly. Oh, no, you can't update it, right? You have to recompute every time you add a value.
No, you can update it. I mean, first of all, it depends. I mean, there are Merkle trees that depend on the order of insertion. Let's call them Merkle trees. I don't know. And then there are Merkle trees where it does not depend on the order of insertion, which are these sparse Merkle trees, right? Where basically every possible element of the tree, of the data set, even if it's not present in the tree, is somehow in the tree in the sense that it's simulated as part of the tree and occupies a fixed position in the tree. And then it's easier to update. I mean, you can still update also a normal Merkle tree, but for those, it's kind of, you have a total ordering always defined on the data set for these sparse Merkle trees somehow. All the elements are always in a fixed position. But for Merkle trees, the witness size is not constant. It's log n.
Yeah, true.
Okay.
Is this what you're doing at your work? Reading papers like this and implementing this?
First of all, that's a professional secret.
Oh, I'm sorry. Is this the type of things you do?
As part of research, there's also, cryptography is not the only thing, of course. Like, it's more encompassing.
Nice. Okay, so you're doing cryptography a bit. A question again. Is this do people actually care about these accumulators though? Like, I mean, is this an active field of research? People want to implement them somehow, and they're trying to come up with or is this done? Is like the RSA accumulator the state of the art, and there's no improvement?
Well, for example, there is another paper where they look at efficient batching. Batching.
Okay.
Like how you can update it at once. I think it's somehow what is the real field of research. I mean, first of all, I'm no expert at all on this, but I think what is the active field of research is more these zero knowledge protocols, right? So you want to have efficient zero knowledge protocols to prove some properties on these accumulators.
Or memberships.
Like, the simplest thing you can try to prove is that you hold an element. So you have an exponent that checks out. That's the simplest thing you can want to prove. But then, for example, this non-membership witness, now you want to prove in zero knowledge fashion that you hold a non-membership witness. And that's already, an algebraic property that is more involved because now you have this weird C to the A equal D to the B times G, whatever. So it's a more complex property. And then you can start, there is work on, proving polynomials, this kind of shit. And, I would say the fancier stuff to do this kind of things are elliptic curves, though.
Okay.
Because I think they're faster. That's
than RSA. They're faster than RSA.
Not super sure. So you use, for example, this pairing. Carlos, cut this, right? I mean, cut this because I'm gonna say bullshit.
No, wait.
But basically, you have.
I think this is interesting. We should keep this.
Why are we cutting this?
No. I'm gonna put swear words every 2 words. If it's interesting, we're gonna talk another time, right?
Okay. If you want to cut it, though, we should summarize and then conclude, and then we can talk if you want.
Yeah.
Also, but you're gonna cut in the middle, right?
We have 8 minutes left, so let's just recap, and we'll say thank you.
Or maybe we should comment on the structure of the paper. Like, I found this incredibly dense.
Really? But it's not. Come on. Oh, you know what is dense? Like, it takes a bit to read the equations that they write. Like, they're super dense. I agree. But once you understand what they mean, they're actually, whatever.
No, but I wish they would have put in the middle like some intuitive. I guess this is how it works in like computer science and math or whatever. Like, it's just like.
But the introduction is intuitive. So all this equation, when you read probability equal to negligible, you should just forget probability. It just means this is impossible.
No, I get it. I think that, like, for example, that I think I understood. And I think if I looked at the math enough, I would understand what was happening. It's just that it was like 10 pages of like, here's the list of things we want and how we're doing it. There was no like.
No, because they're trying to be precise. Yeah, sure.
Yeah.
They want to be precise. In physics, you're kind of more whatever.
No, but I wish there was some sort of, here's an example. Like, the guy comes up to you at the store, wants to check if you have COVID. You give them your.
But they do that. Come on, in the introduction, they kind of do that.
Okay, yes, but I mean, I wish it was like in the steps integrated.
I mean, usually with the RSA stuff, they have like Alice and Bob, you know, and then
Yeah,
like Alice sends G to the K, and then Bob sends like mod, whatever.
I mean, Alessandro is right that they sort of gave you some brief example in the beginning. And I like this too, that they state their contribution, although I didn't check if this is actually their contribution. Like I like bullet points in paper sometimes. But yeah, it was a bit dense for me.
No, but Ale, your explanation was very good, I found.
Yeah, you went through the math very well.
I appreciate
Thank
that.
you, Mom.
And the Merkle tree thing was a nice like context for me also.
But maybe we should summarize the whole thing now. So I guess
you want to summarize? Should I summarize? Or does it work?
Yeah,
30 seconds.
Give us like what's the goal?
30 seconds. So okay. So basically, they expand on the notion of dynamic accumulators by introducing this concept of a universal accumulator that, on top of supporting short membership proofs, also supports short non-membership proofs.
Nice.
It's an expansion in the sense this universal accumulator can still be dynamics, but now being dynamic also encompasses the notion of being able to update efficiently the non-membership witness, because that's what you get on top of that. And then they apply these in a specific context, and in particular, they construct a zero-knowledge protocol that shows that you hold a non-membership witness for an element and an element that is not part of the accumulator, which we didn't cover this time. We may cover next time.